Okay, there we go. As promised, this is going to be a little bit different because, like I said, I thought of several different ways to try and do this, and I realized every single way I tried to do it, you would inevitably have a whole bunch of questions anyways. So we're just going to literally just go through a basic setup for how to do a rotating thing. And we will go from there. So if you didn't already see the announcement, which is fair because I just made it like 5 minutes ago, there is a file on Canvas in the file section, blowerfan.x underscore or underbar t. That is the geometry file.
Super random, but what is that file extension?
Parasolid text.
Oh.
There's also x underbar b, which is parasolid binary. No idea what the difference is. I've only ever used, and I've only ever really seen parasolid text files used as a geometry interchange format for STAR-CCM+.
Cool.
Unless you're going from NX, which is also Simmons. Simmons software works with Simmons software, but if you're going from anything else, parasolid text is the way to go. So it's not too hard to find. There is literally one file in the root of the Canvas files that it has the parasolid extension, so use it. So for the geometry import, and I'll pause after this, is realistically you probably don't need to change any of the defaults. Usually I set it to all CAD edges and turn off merge parts and turn on create one part surface per part. Otherwise, you get a bazillion and a half different surfaces, and it sometimes merges things that you don't want to be merged, depending. And I think everything else is fine by default. It will pop up a geometry scene for us by default. So let me make it so the geometry scene is big enough to actually see. As big as I can possibly make it. And we have our fan. So it looks like just a solid block because one of them, there are two parts in this file. One of them is a solid thing in the shape of the fan. The other thing is the actual surface of the fan. Theoretically, I didn't need to give you the second one, but for ease of use, I gave it to you anyways. So the actual shape of the fan, let me see here, if I go all the way down to scenes, I can only show the one that's relevant. Turn off this one. There we go. So this is more or less what the fan looks like. If you've seen any centrifugal / blower / scroll fans, they probably look something like this. I just literally picked a random image of one that looked like I could probably CAD it fairly well and use the typical blade, simple like thin profile for the blade. This is something that would be used in like industrial ventilation or something similar to that. So clearly this is not in reality one solid chunk. In reality, those blades would rotate. They are not CAD'd as such here, but this is obviously being simplified. So we need to create the CFD model that lets us figure out, based on the geometry here, how much air would it move, how well would it move air, etc. So we need to do a couple things for this. The first thing that I already know, but you could check by measuring things, is that there is no convenient z = 0 plane in this thing. This thing goes from, if I just click over here to over here, and we can look at the output at the bottom. This goes from negative 0.15 meters to positive 0.15 meters in z. Clearly that means there is no z = 0 plane in here, so we have to make one. We have to cut this entire thing in half. So how would we go about that?
Subtract.
You could, A, definitely want to use a subtract operation. B, we don't have anything to cut it with, so we need to make something to cut it with. We can just make a big block and make sure that one face of that block is at z = 0, and we should be good to go. So let me make this window bigger again. So one convenient thing, sort of convenient, depending on what you're doing, is that when you make a block, it auto scales the boundaries to the maximum extents of whatever already exists. In this case, it doesn't really matter. We're just going to put one corner of the box at z equals 0. And for the sake of thoroughness, we're also going to make the box a little bit bigger to make sure it actually cuts off everything else. So it should exactly cut off that half of the scroll fan.
So this one we should only have 3 parts, right? Once this is created.
Once this is created. Technically, you only have 2 parts so far, because that's all that was in the file. But yes, making this block will make it 3 parts. And that is absolutely it. So also, one thing of note, because I am, hopefully it'll be intelligible. I am attempting to record this, so I will post it later, assuming it works. No guarantees my computer will do this entirely free of issues, so it should work, but just as an FYI. So that is a block, and if we want to make a subtract operation, we have our operations folder, the kind of center left-hand side here. So at this point, I presume you all know how to make an operation. If you've gotten away without that by now, it's about time it jumped up and bit you. Oh, did I accidentally create 2 blocks? Oh, I did. Let me get rid of one of those. There we go. Now we have 1 block. Theoretically, having 2 blocks wouldn't hurt anything, but... So if we want to... Well, the very first thing is blower fan 1 was the full block with everything. Blower fan 2 was just the shell with the blades and whatnot. So logically, the way we're going to do this is we want to create an air volume, right? We actually need to create several air volumes, but we'll start with just one. So we're going to subtract away half. I didn't actually hit a target part, did I? We're going to subtract this block away from blower fan 1. And it gives us a chunk of air that is... yeah, we'll do this one step at a time. It gives us a chunk of air that is exactly 1/2 of this fan. This dividing line, I don't know how well you can see that, is exactly on z equals 0.
With the target part being the blower fan 1?
Correct, yes. The target part is blower fan 1.
Sometimes
I was trying to do this earlier, and I also realized it was giving me all kinds of weird graphical things, and sometimes I'd need to like recreate the scene to get it to show up properly, but it would still have worked. It just won't show that it worked properly the first time. You have to like recreate the scene to get it to show. Not entirely sure why. That was also on a slightly older version of STAR-CCM+. So this is the actual current version that you have. But we have 1/2 of our, or well, 1/2 of our original volume, but this plane is at z equals 0. Remember, that's important because this is going to be a 2D simulation. We could do this 3 dimensions, but for the sake of sanity, let's not. 2 dimensions, which means this plane will be our simulation plane. It lies on z equals 0 and is parallel to the xy plane. Well, it literally is the xy plane because it's z equals 0. So now if I change what we're looking at in this scene here, we have just a block. Well, clearly this isn't very interesting. This is just a weirdly shaped volume of air, right? We probably need to cut away everything else from it, right? So we actually have fan blades, the housing itself, that center column, etc. So we're going to create another subtract that does effectively the exact same thing. We're going to subtract blower fan 2 away from the volume that we just made. And again, the way a subtract works is you select every part that's involved, and the target part is the thing you want to have left over. And it will cut everything away from the target part. So let me just create a new geometry scene really fast so we can look at this. New scene, new display or surface. Surface parts, there we go. So let's look at what subtract 2 looks like. Hey look, we have our fan blades cut out. You can actually, if we look really close, we can see all the way through. We have our center column cut out, and we have the housing cut out as well. And if we go back and select blower fan 2 for a second, we can see that that cutout is indeed the negative profile of this. So let me pause for a second and just reiterate the concept of the process that we went through. We started with a solid volume of air. We cut it in half. So we had one side on z equals 0. And then we cut away the fan blades and the fan housing from that volume of air. Does that process follow for everyone so far? And we're left over with this subtract 2. Now, one thing that we probably need to go back and fix is the fact that if we look at this subtract 2, everything is basically one surface. That's not great, right? We typically want more than one surface so we can define boundary conditions and whatnot separately. So, to that end, let's go back a couple of steps. It's not that we're going to undo our work, but we need to do a couple of steps to separate these surfaces. What have we done previously to help with this? Split by patch or split by angle. Some means of splitting the surface. Split by contact if we had things that were touching, but we don't have anything that is interacting for this case. So what we're going to do is just split all three, the block, blower fan 1 and blower fan 2, just split by angle. It'll split off any face that's 90 degrees to itself or to any other face. We'll actually strike that. We'll do that for the block. We will do that for the other one, but for the moment, split the block by angle. It gives us 6 surfaces. No surprise there. It's a block. Blower fan 1, we will also split by angle, which should give us, depends how you want to count them. It's probably going to give us 1, 2, 3, 4 surfaces. Gave us the curved wall of the fan. Let me zoom in on this a little bit. Make it as big as I possibly can. The curved wall gave us one face, another face, and then it gave us the outlet face. So let's actually go ahead and rename this one outlet because it is the outlet, and we will need to know that later. Now, blower fan 2, if we do the same thing, it will absolutely split by angle. It will also give us a bazillion and a half different faces because each and every single one of those fan blades has more than a 90-degree turn in it, right? So we need to be a little bit, I mean, we could absolutely split by angle. Just for the sake of argument, let me do exactly that and we'll see what it does. Has 1, 2, 3, 4, 5, oh boy, that's a lot of faces. 30, 40, 50, almost 60 different faces. We could absolutely still live with this, but I don't particularly want to deal with that. So we're going to do this a slightly different way. And just select all of them and combine gives us back one face. And we can do this intelligently, which is split by patch first. if we split off this base, the inside wall of this thing, we can click on it, it'll highlight just that one, and we click create. It's now made a second surface that is just that face. Oh, sorry, I'm skipping one step. We also need to split by patch and select the other inside wall as well. So select both places where the blades touch. Any guesses why we're doing that? Any guesses why we're making it so we split off the two places where the blade touch into different surfaces?
They're not supposed to have contacts at that point? We don't have any contacts in the meantime, but
Well, it's mostly so that as far as surfaces, they're not connected to anything else. Which means we can split by non-contiguous. And it will give us one face for each fin, each blade.
this is managed on the default floor fan 2 part with the 2 pieces split.
Yes. So now we actually have several different surfaces, conveniently exactly what we'd want for the most part. We have 45 blades. Sorry, not 45. 25? About 25 blades. A central cylinder, and then we have pretty much the rest of it. Well, everything that's not a blade, for me, those are faces 1 through 4. They might be slightly different for you. Those we can split by angle. So the only real important thing is that we have this inner cylinder be separate. And all the blades. Again, if you wanted to do this quickly and slightly more messily, but still pretty reliably, you can just say split by angle and accept that you have 60 different faces. It does absolutely still work. It's just slightly less clean and definitely slightly more messy. So let's see here. If we select all of these, maybe not quite all. There we go. Everything that's fan blade. I think if we say rename, if we select more than one thing and hit rename, we can rename them and it will number them sequentially. So now we have 25 surfaces named blade, and then blade 1 or blade 2. Yeah, blade 2, 3, 4, 5, etc. So we have 24 fan blades as separate surfaces. We have a couple of walls, which aren't the most important thing in the world. And then we have, well, this one might be important. Not really. The one that is really important, though, is, where is it hiding? This surface. It's that cylindrical face on the inside. Any ideas why this one's really important?
Point of rotation.
It is the center of rotation, or the axis of that cylinder is the center of rotation, yes. But that's not why it's important, as a separate face. Sorry, what was that?
It's also a wall.
It's not a wall, actually. It happens to be the inlet. That cylinder in there isn't necessarily there as a shaft. It's there because the air needs to come in from somewhere, and it comes in from the center, gets thrown out through the blades, and then gets thrown to the edge of the housing. So if we look at this, the air actually comes radially out from the center, gets turned and moved by these blades, and then gets thrown out through the outlet up here. It's worth noting, this is a little bit of something that took me off guard. If you see fans that look like this, Sometimes the blades are curved this way, which would seem logical, right? It's almost like they're shoveling air out through that outlet, right? They're sometimes sloped back the other way. They are reverse curve fins. Or sometimes they're just straight fins. And they all work, and fans, they work differently, obviously. But you'll see centrifugal fans and things of all sorts of different curvatures. And they do all work. Don't be confused and see one that's going the other way and go immediately, nope, that's wrong. It might look weird, but it's not fundamentally wrong. It just works differently. But yes, this is indeed this cylindrical face. And again, it might be called this if you've been following exactly along. If not, again, I'm making an attempt to record this. But we can name it inlet. And this is really the only other one we really need to worry about having named. The downside is we did just change a whole bunch of stuff, so we need to rerun our operations. So we'll hit execute all, and we should have our surface or our part with a whole bunch of different surfaces. So let me just select everything here again. There we go. And if we look at our second subtract, which is the beginning of our air volume, we have a whole bunch of different blades, plus a couple of other miscellaneous faces, and an inlet. And as part of our subtract, we have the face that is the block, and we have this leftover face, which is our outlet from blower fan 1. So we have an inlet, we have a whole bunch of fan blades, we have a couple walls, and we have an outlet. Yeah.
So I think this is the first time where we've had an inlet and outlet on different geometry. Is that going to be something that changes anything, or is it still just selected when it comes to regions?
Sorry, say that again?
Like, I think every other lab that we've had, at least in 169 as well, our inlet and outlet was all like the same geometry plane. It was like we make the block for the air.
These will still be two-dimensional.
Okay, so
we just haven't gotten there yet.
Gotcha.
These absolutely will still be two-dimensional. We, however, just need to do more work because part of this thing is rotating. Part of it is not. We need to separate the part that is rotating from the part that is not. So we actually are going to have 3 regions. Even though it's all made of air, we're going to need 3 regions. One for the air that's before the rotating part, one for the air after the rotating part. So first of all, we need to kind of define which part is rotating here. So let me zoom way the heck in. These are clearly the blades, so these will rotate as shown here counterclockwise. So that means that which part of this, let me align view normal to the surface and make this parallel. There we go. Which part of this is rotating? Well, the blades themselves, but it's more than just the blades.
Cylinder as well.
What about the area swept out by the blades? You need to include whatever rotates and whatever volume it passes through as it rotates. So effectively, this is going to give us an annular region, or a cylindrical annulus. Take a cylinder and bore a hole down the middle, right? So there's going to be everything in between about there and there is going to be rotating. Everything inside of that is stationary. Everything outside of that is stationary. But we need to figure out where exactly that is spatially. Like, we can see more or less where it is, right? But we need to actually define where it is. And there's a couple tricky parts to this geometry. Part of that's deliberate because usually fans don't show up on nice, neat axes that are nice and easy to manipulate. The center of rotation is not the origin or any principal axis. for this one. It does rotate around a axis that is parallel to the z-axis, but it's not the z-axis. So one way we can do this is, let's see here, if we, and I do happen to know exactly where it is, but we're going to do this longhand so you can see if you didn't know exactly in space, because this fan might be rotated in some weird direction. It might not line up with anything nice and neatly in your coordinate system. This one does line up mostly very neatly, but we need to see exactly what it lines up with. So one way to do this is to look at you need to look at what the mesh looks like. So what I did is, if we have a scene that shows this part, we can go down to that scene and go down to a displayer that is actually showing the part. So in my case, I made a new scene with a new surface displayer. Or you can just right click and say new mesh scene and hide everything that you don't want to see. Either way. So making a new mesh scene, let me just hide everything that I don't want to see. The only part we really care about is that second subtract part. And we'll see a whole bunch of triangles, really. Literally just a whole bunch of triangles. Now, this doesn't inherently by itself get us where the center of rotation is. But with a little bit of math that the computer will deal with, it does let us generate a new reference frame. Where is it? Let me make sure I'm looking at this right. Oh yeah, a new local coordinate system, excuse me. So if you go down to tools, this one's kind of important. So if you want to write down or, I don't know, follow along. If you're really following completely along, good on you. I'm not worried about everyone following along because, again, this is recorded. Tools, coordinate systems, laboratory, local coordinate systems. This will let us create a new coordinate system. I know this, you might think it's obvious to make this cylindrical. We're still going to make it Cartesian. We're just going to make it centered on the axis of rotation for our fan. So we're going to make a new Cartesian coordinate system. And by default, it just puts it at the old origin. You can see just by me moving this around a little bit, that is very clearly not at the center of rotation of this thing, right? We try to tell this thing to rotate about our base coordinate system, it's going to do all kinds of wacky stuff. It'll still work. It just won't work right. It'll actually probably crash because you're telling it to do physically impossible things with fluids. But I digress. There is a very handy tool at the bottom here, which is define in scene. The one on the left allows you to select 3 points on a plane for defining a coordinate system. The one on the right lets you select 3 points on a circle. Oh, hey, look, well, we have a hell of a lot more than 3, but there's a circle. So we can use this bottom right-hand button, which is select 3 points on a circle, and select 3 points on a circle. Because this is a tessellated circle, don't pick 3 adjacent points. Pick 3 widely separated points to get kind of the best numerical average, so to speak. So let me see here. If you can't really see through the yellow, but there's a small red outline under that. You need to click on specifically some of the nodes. And let me zoom.
Try to lock onto one if you're near.
It will absolutely try and lock onto one if you click. You have to click pretty gosh darn close to it.
God help us on the trackpad.
But you will know it worked if you get a little green, I think that's a hexagon, around the point in question. It's basically impossible to see here because it keeps on rescaling with the screen. But you'll get a little green hexagon around the node. If you didn't get a little green hexagon, it doesn't know what you're talking about, click again. And then go do it 2 more times. The order does matter. It defines which direction is the z-axis, or which is positive z, which is negative z. So if you follow the right-hand rule and basically go counterclockwise, I believe it works out to have the right z-axis. So I'm going to go find 2 other nodes that are widely separated, in this case, approximately a third of the way around. And click on those as well. And you'll notice all the numbers just changed. Most of them are so small as to basically be negligible. The origin, it moved to 0.1904999 blah, blah, blah meters. Well, that one's not infinitesimally small, but the other one is like 3.5 times 10 to the negative 10. I don't know about you, but we're probably not dealing with, what is that, nanometer precision? Micro would be 10 to the negative 6. So this is nanometer precision. Tenths of nanometers. We really don't need that kind of precision. I'm just going to make that 0. Ditto the one below it, which is 10 to the negative 18. Yeah, we are not that accurate. We're also going to make that 0.
Theoretically, if we don't make it 0, is that going to affect anything?
No, it shouldn't. Again, we are dealing with finite tessellation error. For the record, the thing that I happen to know that I'm not really basing this off of, but I'm also zeroing out the insignificant quantities, is that the center of rotation of this thing is 19.05 millimeters in the positive x direction.
And 0 on the y.
And 0 in the y. So these numbers actually agree with that very, very, very precisely. Notice that we're at this point out to something like 9 or 10 decimal places equivalent to 19.05 millimeters in the x. But I am going to zero out everything else. Now, so let me back up a second. To define a coordinate system, you basically need to specify 4 things. Where is the origin? What is the x direction? What is the y direction? And then by right-hand rule math, it knows what the z direction is. So notice the k direction is grayed out. That's because it knows what I and j are. It mathematically determines what k is for an orthogonal coordinate system. It's decided that y is in the x direction and x is in the y direction for this one. It says the I direction, which is x, is almost entirely in the laboratory frame in the y direction, which is on some level fair. It has no idea which way is which other than which point I happen to click first when I was clicking points on the circle. If I had happened to click a point that was almost entirely in the x direction, it probably would be mostly x. So we don't have to guess. Let's do a little science experiment. Let me pick another coordinate system. And this one is going to be almost entirely, or my first point is going to be predominantly in the x direction. Nope, it kind of didn't do that again. Did I? No, I clicked on a weird point. That is a very weirdly canted coordinate system. I don't know if you can see that. Let me go back and try that again. That one. Wait a second. Oh, I know what happened, I think. Anyways, let me get back to something that makes a semblance of sense, and then we will be back on track. Okay. Not quite as accurate as I'd like, but same principle. But if you don't know the center of rotation, but you have a rotating thing, well, it's a rotating thing. It's going to make a circle somewhere. You can pick multiple points on that circle to define your coordinate system. So in this case, let me just override it. And for the purposes of this, you can just use the exact value of the origin should be 9. In terms of meters, the origin should be 0.01905 meters in positive x. You can just leave the x direction as 1, 0, 0, and then 0, 1, 0 as the y direction. And it will figure out everything else. Oh, maybe that's why it was acting weird. Anyways, so our origin is, you probably can't read that, again, 0.01905 meters in x, 0 in y, 0 in z. The I direction is just 1 in x, 0, 0. The j direction is 0 in x, 1 in y, 0 in z. Yeah.
So with those updated lines still got y in the negative x and x in the...
Renormalize at the bottom when you're done. Does that fix it? Yeah. When you're done changing things manually, hit renormalize and it'll redo the calculations to fill in the blanks. Because hypothetically, you could type in like, I don't know, 510 or other weird stuff and hit renormalize, and it'll like do weird things with the coordinate system by recomputing. Let me fix what I just deliberately broke. 10, renormalize. So renormalize just has it redo the calculations to make everything a unit vector and all that other good coordinate system stuff to make sure things are self-consistent. But again, if you don't know what the center of rotation is, you can use the 3 points on a circle method to find it. If you do know what it is, you can type in exact numbers and make the center of rotation, the axis of rotation, exactly what you want it to be. If you know it, use exact numbers. If you don't know it, you can find them to a very high degree of precision with the 3 points on a circle bit. Once you hit create, it creates a coordinate system. It will not automatically close the dialog. So if you hit create a half dozen times, thinking it's going to close, you're going to have a half dozen coordinate systems. They'll all be the same. Just create one of them. And then you'll have a new coordinate system. I'm going to rename this one a fan axis because it's centered on the axis of the fan.
You're saying it was a tessellation error due to the geometry. If we were to like actually create the mesh for this and then do that, would it potentially be more accurate?
You still have tessellation errors.
Okay. So
you have tessellation errors because these triangles that you're seeing right here,
right.
Those are what define the surface.
Right.
When I exported it from SolidWorks, those are the triangles it made. SolidWorks didn't say it's a circle.
Right.
SolidWorks said it's a whole crap ton of triangles arranged in this way. That's what a tessellation error is.
So you can't mitigate that at all, even with like new mesh or like remesh it?
The only way to mitigate that is if it is directly talking to the CAD software.
Okay.
And it is able to, the CAD software, they're able to communicate in such a way that the CAD software says, this is a circle. And STAR-CCM can interpret that.
So coming from like NX?
Coming from NX, it would remove all tessellation error because it would know not just this is a shape made up of triangles, it would know this is a circle,
cool.
Or this is a cylinder, or this is a sphere, or whatever. That can remove tessellation errors. But if there's any type of communication or like file translation involved, it almost certainly can't. Let's see here. So the important thing is we now have a fan axis. This is going to be very, very helpful on a couple different levels. But perhaps most importantly, because it lets us define cylinders that we can use to cut this air body into different sections, because like I said, we need 3. We need an intersection, which is stationary. We need a rotating section, which encompasses the volume of the blades and the path they sweep out. And we need another stationary section outside of those blades. So we're going to need a couple cylinders here. And we are going to need to do multiple subtract and other operations one after another to create what we want. It's not all that hard, but you have to think of from the terms of the tools that you have, which are basically unite, subtract, and there's a new one called intersect, which is going to be very useful for this. Not new in the sense that it's always been in STAR-CCM+, but I don't think I've mentioned it before. It is a very cleanly defined mathematical operation as well. So first of all, we need to find out roughly what are the extents of these blades in our y direction. I say in the y direction because the y direction is the same for both our coordinate systems. So we have a little ruler tool. Let's use it. And let's click at the very end of one of these blades. And also click at let's click at the top of this blade as well. So, let's see here, can I zoom? Aha, larger text. That might actually be sort of readable. So, there are a whole bunch of numbers here. Which one of these actually matter? Well, this first line is the coordinates of the point I clicked on first. The second line is the coordinates of the point I clicked on second. Clearly, the z doesn't matter. That's basically 0 for both of them. Again, tessellation error means it just thinks it's, 1 times 10 to the negative 18. But that's just tessellation error. There's a small x deviation, but that's really not particularly significant. The thing that is significant is the y difference, because I was trying to click on a blade that is, let me rearrange this again, was mostly aligned with the y-axis. So this minimum y value is probably pretty close to the minimum extent of the blades in y. The maximum is probably pretty close to the maximum. So what are the size cylinders we need to make to cut this thing away? For record, that first one is 0.0768 meters, and the second line is 0.1058 meters.
We want to go just past them?
We want to go a little bit below the minimum, a little bit above the maximum. Now, how much depends on, in part, how close anything are to the blades. Some blades get extremely close to the walls around them. You might need to get really, really close to the tip of the blades if you have something that is stationary right next to them. But we don't have anything stationary that's right next to them. We can afford to go a little ways away. So let's try and go 5 millimeters out in both directions. So that means we're going to need 2 cylinders. One cylinder that is, call it 72 millimeters in diameter. Oh, excuse me, in radius. My bad, not diameter. And the other one that is probably about 111 to 112, somewhere in there, millimeters in radius. What coordinate system do we want these cylinders in?
Our reference.
Which one are we referencing?
The axis that we just made. The fan axis.
If we just made it by default, it's not. Let me zoom out again here. If we just made it as is, this is very not centered on the fan. You can see the axis that it's going to make here, and that is not in the middle of that fan, right? So we do indeed need to use the new fan axis coordinate system, which, hey, look, that's in the middle now. Makes it nice and easy. So we are going to actually make these a lot longer than we need to, because we're going to use the intersect command. And we want to make sure these entirely encompass the air volume that we already have. We're just using these to effectively select volumes of space. These aren't actually going to be volumes of space by themselves. So effectively, we're making a tool that we're going to use to manipulate what we already have, not actually making anything new. Literally all of the resulting geometry we have for the air is all going to come from that one part, that blower fan one part. Everything else we're making is just a tool to manipulate it. So I already forgot what numbers I said. So we need the first one, the inside one, to have a radius of probably about 72 millimeters. Oh, hey, look at that. We have, if I zoom this a little bit, it's a little bit hard to see, but if I get this just so, we can see that the cylinder stops just inside of the blades, which is exactly what we wanted. So we can click create there. And the other one we said probably needed to be about 112 millimeters. And this is harder to see for several different reasons, but let me see here. This ends just outside the blades. Can everyone see that? How we have a gap between the outside of the cylinder and the blade. And then also importantly, if we go look at the side over here, we have a gap between the cylinder and the stationary wall. Oop, I just need to re-input all of these because it just changed a bunch of stuff. Okay, to keep things simple, I'm just going to make a copy of the cylinder and change the radius. There we go. So we have two cylinders. They're way the hell longer than the fan is, but that was deliberate. Now we need to make the annular cylinder that encompasses the blades. If we have two cylinders, how do we do that?
We only want to do encompass the blades. Subtract one from the other.
We can subtract one cylinder from the other. So another subtract operation, and I'm attempting to not take an age and a half with this, so I'm not, but best practice would be to name these things as you go, so you know what the heck is what. So if we select both cylinders, the bigger one is cylinder copy, so that is the target that we want. This will subtract the smaller cylinder from the bigger cylinder, and will leave us with an annular one right there. So now again, we want three regions of air. One inside the blades, one outside the blades, and one encompassing the blades. We actually already have everything we need to do that. We just need to set up a couple more operations. But we need to talk a little bit about one of them first, because I haven't really, and that is the Boolean intersect operation. Any guesses what this one does?
Makes connections based on the intersection of the selected parts.
Doesn't make connections. That's imprint. You give it, it has one list of parts that you give it.
Spit out new.
It does indeed spit out a new part.
Based on what's intersecting between the list.
I believe the way it works is that this works either one of two ways. I'm not actually 100% sure because I usually don't use it. But if you only have two parts, the output will be only where those two parts overlap. Where the parts do not overlap, there will be no result. Where they do overlap, there will be a result. I'm unclear if you add more than 2 parts, if it will only output a part where all of them overlap or where any of them overlap. That's a distinction I haven't really needed to test. Although we can actually test it. Yeah, screw it. Let's find out right now. Easy enough. So I'm just going to select all our cylinders and our block and just see what it does. Okay, it's only where all of them overlap. Because I just selected the block and 2 really big cylinders, and the only region that it produced is one where all 3 of them overlap. So intersect will only produce a part, will only produce a result where all of the input parts exist simultaneously. So for us, if we want to have just a air region where the fan blades are, we have our annular cylinder, which was subtract 3. And we can intersect that with subtract 2, which was all of our air. Where those overlap, hey look, we have an annular region of air that has the blades inside of it, with the blades cut out of it. Now, how can we get the inside air volume? We have several different parts. All right, we have a small cylinder, a big cylinder. We have our total air volume. We have just a block of air. We've got several. We also have our random block, although we're not using that one for this one for sure.
Do intersect with subtract 1 and 2?
Not 1 and 2. But we can do a subtract between the second subtract, certainly, and our first cylinder. Because the first cylinder is the small cylinder.
So intersect between those 2.
Intersect. Because remember, nothing that's in this small cylinder showed up in that first intersect. Because this small cylinder was subtracted away from that annular region. So with the way things are defined, literally nothing can overlap between these if we do a intersect between our subtract 2 and our small cylinder. And if we look at intersect 2, we can see that it is indeed this annular air region inside of the other one. Now, again, depending what type of fan you're looking at, this in principle works just fine for axial fans, but those have to be 3-dimensional by nature. This is a blower fan, which kind of works 2-dimensionally, at least sort of, which is why we're doing this. But the exact same process, if you have to create a region for the air basically in front of the fan or around the fan, depending, is if you have free spinning blades or even blades in a housing, the blades can be entirely encapsulated in a region of air that rotates, and then everything outside of that doesn't rotate. But you always need multiple regions of air. In this case, we're building 3. One before, one rotating, one after. But the same principle holds regardless of what you're doing with rotating blades. And also regardless of how you're doing it. There's multiple ways of simulating this. All of them need this to be a separate region. But lastly, we need a region after the rotating blades. Again, air flows from the middle to the outside. So how can we do that one?
Another intersect.
Actually, no. Not for this one. We definitely need another operation, not an intersect. Although I suppose if you got clever, you might be able to do an intersect.
Unite?
No, it can't be an intersect. There's no way to make it that work. Unite doesn't work either because you need to combine multiple parts. That produces a result that is any part, right? You can think of a unite as any, a logical any or. A subtract as a logical not. and they intersect as a logical AND. The output of an intersect will only be where all the input parts overlap. A subtract will be where they do not overlap. A unite will be where any of the parts exist. So you can kind of think these as logical operations, which is why they're called Boolean. It's because they effectively are logical operators in that sense. At least some of them are. So we have a small cylinder and a big cylinder. If we subtract the big cylinder away from our air, that should get everything that's not inside of it. So Boolean subtract, our big cylinder is the copy, and our air is subtract 2. So if we subtract the big cylinder away, our result, theoretically, is everything that's not inside the blades or inside of them. That's not the blades or inside of them because we subtracted away that big cylinder.
And our target is the subtract 2?
Yeah, the target is the subtract 2. So we got a kind of weird list of things, and we definitely want to name them now. Otherwise, this is going to get really confusing, right? Like, which one is which? Intersect 1 is what one again? Like, the answer is it's been recent enough. I do remember what it is, but I'd rather not have to remember for the entire time I'm working on this. So let's go ahead and rename all of these. Any ideas what we should name this one? We could rename it all kinds of things, but this kind of gets into a quality of life thing for yourself later. It will frequently alphabetize things. Air fan or air rotor or air rotating might be a good example, and then we can name the other ones air of something, and they will always show up right next to each other. And more importantly, they'll always be at the top of the list because they start with the letter A. So I'm going to name this one air. Yeah, we'll call it air rotor. Air inside. It's probably good enough. I'm trying to see if I can get a good one that will put these in alphabetic order from first to last.
Which one do we want first?
Inlet. Generally order them from in the path of the air. So the path is going to start at the inlet, go through the rotor, and then go to the outlet. The problem is that doesn't work alphabetically.
Air posterior.
Yeah, I suppose that would work. Wait, actually, no, it wouldn't.
No, not behind rotor, crap. Air out.
Pretty sure that also doesn't work with the alphabet that way.
We want, in the out.
Technically, this fan doesn't have a stator. The stationary blades in a fan. But we'll call it air stator. If you ever look at a jet engine, the stator is the blades that don't move. The rotor are the blades that move. Or any sort of compressor or rotating turbo machinery. If they're stationary blades, it's a stator. If they're rotating blades, it's a rotor. But conveniently, we have, if we put them in this order, air inside, air rotor, air stator, it puts them in the logically correct order for us. We do have a couple of contacts. They don't actually matter. These are not relevant for us. So we need to do an imprint to get the ones that are relevant because we just made the connections. We just made the surfaces that we want to be touching, right? What surfaces do we need to interact? I'm just going to highlight this one because realistically, this is the only one we need. Where are these going to interact?
So we need the rotor touching the inside and the rotor touching the stator.
Yeah, you have one interface right here where the inlet air touches the rotor, and then you have another interface where the rotor touches the what I'm calling the stator air or the outlet air. So clearly we don't have either one of these. So let's do a new Boolean imprint operation on, oh, hey, look, at the very top of the list, we have air inside, air rotor, air stator. We can go straight to the top of the list and just select the top three and be done. We don't have to search through a random list to find them. They're nicely ordered at the very top. So we can do an imprint and see if it did what we need. Well, yes and no, or sorry, yes, but it may not have. Theoretically, it could have tried and failed or done something. So let me deliberately mess this up so you can see what I mean. Execute. Does that look right?
Looks cool.
It looks interesting. It definitely doesn't look right. Right. If you saw an imprint that looked like this, you'd be like, okay, that didn't work. Something's wrong. Let me go try and figure out what's wrong. But you know it's not right. Ditto the outside. Like, it's got all these random, like, it almost looks like somebody wrapped a barcode around a cylinder. Doesn't make very much sense.
Wait, if you highlight the mode, does it make one complete? Like, it almost looks like they...
So what I did to break this is I told it only create a imprint / a contact where they are exactly matching, which means it was much more precise than it needed to be.
So if you were to be coming from NX, though, would that once again?
That would absolutely work just fine if you were coming from directly from NX or something. But because we have tessellation error, these things aren't exact matches in a lot of places. They were still exact matches in an awful lot of places you saw, just not all of them.
If you drop the tolerance way the hell down, that would still potentially work, right?
Potentially, but there's another version for that, and that's called a discrete imprint, where it actually is aware it's like, okay, these things are made up of triangles. This is a discretized geometry. That is, it's been tessellated. With that in mind, let's do the imprint, or the computer does the imprint with that sort of precision, which by default is 1/10 of a millimeter. That's usually pretty good precision for most things. And sure enough, if we look at our faces now, these sure as hell look like continuous cylinders. That look like that to you? Solid cylinder? I don't see any gaps, so that looks pretty good. Yeah.
For sanity, you have not saved maybe ever.
You're quite correct. I know I haven't because it still says start one. Thank you. I hope that I'm thankful that wasn't already a problem because we do not have the time to do this again. And I do not have another copy of this handy. So that would have been particularly unfortunate. In any case, so now that's our geometry. And it took a fair bit of preparation, but we started with two parts that you've all been provided: the geometry of the blades itself and a matching region of air that overlaps with them. Right? We processed it in various ways. We cut the solid away from the air region. We separated it so we have a z = 0 plane. We made a region specifically for the blades, for the air inside the blades, and then the air outside of the blades. And realistically, this is the end of our geometry preparation. This is what we need. Oh, and we made the contacts between the three regions that we created, or three parts that we created that will be three regions. So that's kind of the end of our geometry preparation. We do need to create the regions, so let's go ahead. Oh, actually, we're missing a step. We do need to make this 2D. So if we go to, we can make a badge for 2D meshing operation, just like you've done several times before. And select, hey look, our three air regions are nice and neat and at the top of the list. You can just select those three and ignore everything else and tell it to badge for 2D meshing. And check to make sure it got it right. It's not yelling at us. It just says it completed in basically 0 time. It was like 20,000th of a second or something like that. And if we look up here, this is one way to verify if it worked or not. do you see a little red dot next to the things you tried to make 2D? If you do, then it worked. If you don't, then it didn't. Usually the reason it didn't is if you don't have an appropriate plane or a surface on the appropriate plane is the usual reason for it to break. But it did indeed create our 2D domain based on this, so we can select all three of these and turn them into regions. Again, the way I do that is assign parts to region, create a region for each part, create a boundary for each part surface. That one is important. And at the bottom, the default of create boundary mode interfaces from contacts is fine. That means it'll take every contact we just made and turn it into an interface. We just verified we had the proper contacts, so in theory, we should have our regions. Hold on, let me create a new scene so we can guarantee that this is doing exactly what we expect. New displayer. So I'm making a new surface displayer that only looks at the regions. If it shows up here, it's a region. If it doesn't show up here, it's not. There we go. And this is also 2D, which is a little bit weird. So, actually, tell you what, let me make a new, no, apply representation. Okay, so notice how we don't have any facing surfaces. We have a whole bunch of blades. We have our inlet right here. You can even see it's named inlet if you look close. We have our interface between the inlet region and our rotor, which you can see does have an interface associated with it from the little green line there. We have the interface between our rotor and our stator. Again, stator is a little bit of a misnomer in this case, but I'm going to stick with that nomenclature for this one. And then we have an outlet, and we have our walls, and we're able to select them all separately, which is good. We can also select any one of these blades that we'd like. And they're all separate. So it indeed created a two-dimensional air region that looks like it's exactly what we want. So now comes the really interesting part. We need to mesh this. So this could definitely get interesting. We probably want to mesh these three separately, or at the very least, we want to mesh the inside and the outside separately. We want to mesh the rotor as something different. So I'm going to, let's look at the inside and the outside first, and then we'll come back to the rotor, okay? I hate how it cuts off my OK button at the bottom.
You don't need that.
I mean, I can just hit enter and it works just fine. But so for 2D stuff, the usual recommendation I have is to do a polygonal mesh with prism layers is usually what works best. So we need to select a base size. Well, how big is this thing approximately?
Oh, it's 0.3, right? 0.3 meters?
It's 0.3 meters in Z, but Z doesn't matter for mesh. We only care about X and Y.
A little tricky though. It looks like it's also about 0.3.
0.32, give or take. Yeah, a little bit over. It's almost exactly 0.3 in the Z direction, which is why that is a little bit confusing. But how big do you think we might want to make the base size? Approximately. Oh, probably a lot smaller than that. In an ideal world, like if you just broke this up into completely uniform cells, how many would you need to have an idea of what was going on?
I like 100,000. Yeah. How much time do we have?
I mean, good question on all accounts, really. It's a complicated one, right? There's no really hard and fast way. A centimeter is almost certainly too big. That only gives you 30 across. That's almost certainly not enough. A millimeter is probably too small. Just keep in mind, this won't be the smallest you go. This is just kind of your baseline. This is like the maximum cell size by default, unless you tell it something different. So a millimeter is probably too small. We're probably looking somewhere between a half centimeter to like 2 millimeters in that general neighborhood. Just based on the rough size of this thing, and a half centimeter will give us 60 cells across, roughly, right? Which is probably about right. It might not quite be enough, but it also might be. So it's probably somewhere between about a half centimeter and 2 millimeters would be a good estimation. I'm going to start with the bigger size, which is a half centimeter, because if we mess it up, it won't take forever for it to mess up. So you tend to want to mess up with cells too big and walk your way in, rather than mess up with cells too small and sit there for 2 hours to figure it out. I don't know if any of you have done that before, but that is the danger of making cells too small by accident. So our base size of a half centimeter kind of puts a ceiling on the number of cells we might potentially have. The target size of 100% is usually good. That's why I typically pick my base size of about the maximum size that I want, so I can just leave target size as 100%. You could also mess with target size. I know it drove me honestly kind of crazy. But at my previous job, a lot of people would just leave the base size alone, and they would mess with the target and minimum size separately, and they wouldn't touch base size. I prefer to set the base size as approximately what it should be, and then do any tweaks from there, rather than leaving base size at 1 meter for something that's definitively not a meter.
Does it give you one cell if that's the case?
No, at that point it would give you something that it would probably just yell at you and break, honestly. You know what? Just hell, for the sake of argument, let's try. I can virtually guarantee this will just do that. Like, it tried real hard, and it's just like,
I like it.
you have a grand total of like, I don't even know how many cells. Not enough.
Did she tell you, right?
I don't even know what's like, what? Oh, keep in mind that hole in the middle is no, it's a hole with a pizza. Well, the hole in the middle is now a pizza slice. Yes, the outside, it's bad. It will do something like that. I don't know where it would break exactly. I'm actually kind of impressed it did that much with a 1 meter base size, but wouldn't tell you anything, but you could. Hell, that's how fast it's already done. I just gave it half centimeter base size, and it's already done. So, like, realistically. Now, to be fair, this is not where we're going to stop, but that's a very good starting spot, in my opinion, right? We just gave it half centimeter, and it worked pretty darn fine. It actually ran fast enough. I'm going to knock that down to 2 millimeters. We don't need. Even better. So we're probably going to want some controls on this to make it do more what we want. So what are the usual controls that we typically do? Well, surface control, but on what?
Walls, we define far field, but I don't know if far field's going to be better.
Well, the far field's actually a wall in this case. It's also not particularly far. It's right there. So we probably don't need to mess with that at all. But we do want to mess with the inlet and the outlet, for sure. So let's start with those. At the very minimum, we want to turn off prism layers. All right. So we can, this is a short enough list of things. It just gives us a list of things. One of these is called inlet. One of these should be called outlet somewhere. Oh, well, it's not actually super readable in that list. So let me dig into here. Cylinder copy. Wait, was it this one? No, it is. That's it, all right. I'm not sure why it called it that, but whatever. Anyways, that's our inlet on the inside. And, oh, I picked the wrong one on the outside. Sorry. That's not it, actually. Where is my inlet? Oh, that is the inlet. Where's my outlet? That's what I meant.
On blower fan 1?
No, it's on air stator. It's part of the...
Right, and then the subtract. Yeah, blower fan 1.
Oh, yeah.
Right?
It's just called blower fan 1 because it only had one surface. You're absolutely correct. So you were keeping better track than I was. I should have named it something. I thought I named it something, actually. Hold up a second.
Pull it back.
Inlet.
You're on blower fan 2 now. There it is.
I named it outlet. Why isn't it called outlet?
Oh, mine is.
Whatever. Anyways, we figured it out. So we have our inlet and our outlet. What do we want to do? Again, the way any control works is you specify where, in this case on these surfaces, and then what you want to change, and then how you want to change it. So what do we want to change? Well, we probably want to turn off the prism layer because these are theoretically free air boundaries, right? On the other side of this boundary isn't a wall, it's a fluid of some kind. Presumably still air, unless something really exotic is going on. So we'll go ahead and disable prism layers. That's one thing of what we're changing. We don't need to define any value because we just said turn it off. We could change the target size and the base size, or the minimum size. That might be a good idea. Let's go ahead and turn the target size down to like 50%.
We didn't change anything but the base size on the initial, right?
Correct, which isn't necessarily what I recommend, but we'll need to circle back around to that. We will need to change more stuff there, but so yeah, just turn the minimum surface size on these down by a factor of 2. Speaking of, we probably also need to change our prism layers because 2 usually doesn't cut it. Depends on what you care about, but in this case we care about things that means we care about prism layers and boundary layers. So let's use 8. We don't care quite as much as if we do for an airfoil because the blades aren't in this region, but we do still care a fair bit. So we'll use 8 prism layers, and usually when you knock up the number of prism layers pretty substantially, you also want to knock up the thickness of the prism layer region, because if you don't change, you know what, actually screw it. Let me just leave this as 33% and let's mesh this again and see what it looks like. You get some pretty serious discontinuities between the size of the cell and the size of the cell just outside of it. So let's make this like 75%. Usually it's not possible to mess with this so quickly, but because we're dealing with this, it works a lot better. And that's a much better agreement. This last cell is several times thicker and isn't the same size, but is approximately the same size as the cell immediately outside of it. Even these smallest cells, like these cells are smaller than this, but not tremendously so. So this looks like a reasonable agreement. And then we have little tiny cells on our inlet. We have also little tiny cells on our outlet. We also have prism layers here. Well, this is an interface, right? We probably want to do something about that. But we also probably want to keep cells from growing quite this much. These are some big cells just hanging out in the middle here, right? So let's deal with the big cells first, and then we'll worry about this interface here. So how do we make these cells stop from growing too far? It's not a wake refinement, it's a surface control. But remember, this is a 2D simulation. So the planes that we're simulating on are surfaces. So if we break open this list and see the ones that are outlined with, or not outlined, they're like the solid red sheet. That means those are the simulation planes. So I selected both of them. They're named something effectively random. But you can see that it highlighted the plane that we're meshing. Incidentally, if you weren't already, you can click on the surface control and it will show you what surfaces or what volume or what curve it's looking at. So we can just tell it on this entire surface, make the target size like 175%. And theoretically, it should stop any of these cells from growing more than 175% of the base size. Now they grow a little bit, but they're all pretty uniform. Oh, the other thing is I forgot to turn down the surface growth rate. It's, again, stupid fast by default. Usually I override it and use 5% growth rate. Well, now this prism layer is a little bit wonky over here. You see the issue here?
Back to 60.
Yeah, I'm thinking that if we drop it back to 60, it ought to work pretty well. Maybe not perfect, but better, certainly. It looks really bad, but that's because we're cutting off most of the cell. It's a little bit more reasonable if we look at the typical cell size there. So that's probably okay. And then it's also pretty reasonable out here. So we'll call that good. I don't know why the cells are so small over here, incidentally. It like picked a couple of random spots on the circle to make the cells noticeably finer, but in any case. So now we probably want to mess with these two interfaces. This is another surface control because they're surfaces. Now figuring out what surfaces there are is going to be a little bit interesting. So theoretically, I happen to get lucky. It is one of these cylindrical faces on that one. And theoretically, it's the other. There we go. Yeah. So I guess the easy way to see that is they are child surfaces of this cylinder. So if you see a cylinder, or in my case, cylinder copy, you know their surfaces associated with that.
They're like a hollow red shape if you were on that drop-down tree.
Correct. Yeah, that's a perimeter of the 2D domain. The solid red shape is the 2D domain. The hollow red shape is the perimeter of the 2D domain. Why do I have two of these? Well, we definitely need to change a couple of things. The first of these is probably the fact that this prism layer should not be like this. Now, this is a little bit weird. We know that on the other side of this boundary, there is air, right? This is where two regions of air are touching. But we still want a prism layer there. Because if we have a prism layer there, then the cells on either side will agree very precisely. So what we can do here is, this is hard to see, but we can customize pretty much everything about the prism layer. We can customize the number of layers, the total thickness, and the distribution there. And there's other parameters that we can modify as well, but really those are the big three. again, prism layer thickness, the number of prism layers, and the prism layer stretching factor. I'm going to make the prism layer stretching factor 1. What does this mean?
It'll be the same thickness as the previous layer.
Each layer in the boundary layer won't stretch. If you set it to 2, that says each layer can grow by a factor of 2. 1.5, it can grow by 50%. You set it to 1, it can't grow at all. They all have to be exactly the same thickness. Usually this is not what you want for a boundary layer. Oh, why won't it take that? 1.0? Oh, non-inclusive. Okay, we'll do 1.1. It'll grow a little bit, but not by much. And we'll do 2 prism layers. And then roughly how thick should they be? Probably about 50%. So you will see the reason for this, but we'll have to mesh the other side of this first. The entire point of this step is to make sure the mesh on both sides of that interface agrees very closely. And we can ensure that by using the same prism layer parameters on both sides. Prism layer is not the only thing we want to modify. We want to make this mesh really small here. So modify this down to 25% at the interface for the target size, and the minimum can be like 5%. We're letting the mesh get really small at this interface, and you can see it's taking a second. Still running pretty fast, but it's taking a second. 4:30? Yeah, we got time. And we might want to turn down that prism layer thickness a little bit. You see this? This is a sign, I mean, we're basically not stretching the prism layer at all. This is a little bit of a size jump. We can fix that a little bit. We make the prism layer like 25% thick, I think. Or we don't need to constrain ourselves to factors of 2. We'll do 30% thick and see what that does. But if we make the prism layer a little bit thinner, these will agree a little bit better. There we go. That's pretty good, I would say. And we get basically the same thing on this side. Okay, now we need to do the blades themselves. This is a different, probably just a different mesh operation entirely. Like theoretically, you could set this all up in one mesh operation. I don't particularly recommend it because you'll have to fiddle with a whole bunch of custom controls. Really? Okay, fine. There we go. So what I just did is I made a second automated mesh operation, and it is pointed at the the rotor region. For consistency's sake, I'm going to give it the same 2 millimeters base size. So if we want to tweak one versus another, we can change the base size to get the relative size difference. But if we set the base size the same, theoretically all the controls should map to itself perfectly. Just for grins, let's just run it and see what it looks like. Except I need to make a new mesh scene because this one doesn't know what I'm talking about. There we go. Okay, we got some issues with this, I would say. We probably need these to be smaller, right? I mean, you can see rotor, stator. These don't agree very well. So we probably need pretty much everything in the rotor to be smaller. We can do this a couple ways. We could turn down the base size. I think what we should do instead, though, is turn down the target size. We'll start with 50% and then see what it looks like. And then we'll kind of make a call from there. I think 25% is probably more appropriate. I just don't want to. Yeah, 25% would be better. Actually, sorry. There's one thing that we're missing is that these cells are growing, again, stupid quick by default. So let me turn down the growth rate to like 5% again. Oh, nope, not 1.5, 1.05. There we go. Getting there, looking more reasonable. We could probably work with this as a baseline. However, we do need to figure out a couple of things here. The first thing is we probably want these to agree very exactly. So let's create a custom control. A custom surface control, which should be the surface of. Wait a second here. It's not any of our blades, we know that, so it's got to be this one. And then, or not, it might just be both of those. Yep, there we go. It's both of our cylinders. So both sides of that. We're going to set it to the exact same thing that we had on the, as a matter of fact here, hold on. Let's be intelligent about this. We have that exact same control up here, right? Let's just copy it. No need to make our life hard. Just literally copy and paste. And just point it at the right surfaces on the inside. And theoretically, this should get very, very, very close to the same thing. Potentially even down to the level of individual cell nodes exactly matching. It's not quite that close. They're offset by like a factor of 2. So let's look at this really, really close. Yeah, these all seem to be offset by pretty much exactly 2. Is there something to do about that? Or exactly 1/2?
But your inner or your outer connection? So my outer is almost dead on, my inner is half.
Both, actually. See? Theoretically, it's probably still going to work just fine. Ideally, I'd like to see them perfectly lined up. I wonder if it's just walking as it moves around the circle. But it doesn't look like it is. It looks like it's just off by exactly a factor of 2.
Could be a sizing issue. Because I mean, the cells inside look a little bit larger than the ones on the outside, so maybe
they're the same target size. Because remember, part of this control was a target size of 25%. Give me just a second here. I'm pretty sure there is something to do about this, but let me see here. We'll see if this fixes it. If not, it's just something we'll live with. If you can get them to exactly line up, that's ideal. But theoretically, it should still work. Oh, right. It's running both mesh operations. Nope, they're still off by a factor of 2. I'm not sure what it is exactly. We'll go with it as is because, again, theoretically it should still work. But what the heck do we need to do about these blades? Because that is probably not right. So we need more prism layers, I can tell you that to start with, right off the top. We probably also need a finer mesh on the blades. Like, it can grow more. Or it can grow probably about as much as it is, honestly. But we definitely need a finer mesh on the blades. So what would that be? We can probably just change the target size, right? Use everything out. Literally, this region has effectively 3 types of surfaces. It has the inside interface, it has the blades, and it has the outside interface. We're already telling it what to do for the interfaces, so we can just change the default properties, and that should affect the blades, and only the blades. So we already set the target size to 50. We'll set it to 25 for this one. But we also need to mess with the prism layers a little bit. Any thoughts on that one? Possibly.
I think you thought you had it 25.
Okay, well, we can test this theory. Let's put the target back to 100%. It's going to mess up the blades. But if it fixes this, we can make a new custom control for the blades. It'll be fine. Doesn't look like it changed anything. So we'll just live with it. So that said, I'm going to put the blades back to 25% for target size. But prism layers. Thoughts? We definitely need more prism layers. So let's turn up the number of layers. What's a good value? Probably 12, because theoretically these are interacting with the boundary layer a lot, right? They're moving quite fast in proximity to other things. 12 might be a little bit overkill, but I would rather go too many than not enough. Especially because depending on how fast this thing is spinning, these blades might conceivably stall, which would be highly dependent on boundary layer behavior. So we want more boundary layer resolution, not less. The prism layer stretching of 50% is probably fine. Prism layer thickness. Keep in mind this is relative to base size, and we're turning down the target size on all of these pretty far. So maybe even just 25%. Like, that's a guess, but remember this is 25% of the base size. And we're also turning down the cell size on these blades by a factor of 4. Right? Because the base size is 2 millimeters. That means the target size on any of these blades is going to be 0.5 millimeter. Which also means, in turn, that a boundary layer thickness of, I can't even read that. Hold on. Like, I can't read that. So a boundary layer thickness of 0.5 millimeter is the same size as the cells. Like, honestly, 25% is probably still too thick already. So this is weird. 25%? We'll see. This is a little bit, you might just have to, unfortunately, do a little bit of trial and error and figure it out. And I think that ought to just about... Oh, there is one more control we're going to want. We want to set the maximum size for any cell in the rotor region. Same thing. There is one of these. One of these that is... what's the word I'm looking for? In this case, it's part of the block, which is our domain itself. You can see it selected everything about this entire surface, right? Just check. Yes, it is still recording. Perfect. I also save before I forget about it. There we go. We can just set the target size for this to, I don't know, what might be a good value. Keep in mind this is going to be the maximum size for literally any cell in the rotor. $50 might be a little bit aggressive. It's probably between about 75% and 100%. Keep in mind this will make sure no cell gets small. 100% makes sure it doesn't get smaller than 2 millimeters. 2 millimeters is already pretty small. So we'll start with 100 and see what it does. The answer is 100 might not do anything. We might turn it down a little bit past that, but we're going to start coarse and then let it get small. This mesh does run pretty fast, but again, we do have limited time, so.
Yeah, Sharpie highlights on Zoom.
That looks pretty reasonable. There's a little bit of weirdness going on at these sharp edges, but you just kind of always have that, honestly. You're really not getting away from it too much. Like we could let these cells get smaller, but we just have the same effect smaller. So that's honestly probably pretty good. So we have our mesh, we have our regions. We do not have our continuous set up. It made one for us when we meshed it, but we need to select what type of physics we want to use. So, what type of physics do we want to use?
Gas.
Okay. Now let's go ahead and select gas right off the top. That one's pretty obvious. Theoretically, this shouldn't be going all that fast, so segregated flow is probably just fine.
Ideal gas?
Ideal gas, we can do the ideal gas based on temperature, so it'll let the density change a little bit. Theoretically, we could noticeably compress air running it through a centrifugal fan because it might locally change pressures quite significantly. This one really depends for any turbo machinery purposes. In this case, we'll go with steady. There are frequently very good reasons to run an unsteady simulation for rotating machinery. Yeah, for anything that's rotating, any sort of turbo machinery. We will go steady for this one to try and keep our sanity intact. But there are very good reasons to use unsteady flow for these. This is probably a little bit of an oversimplification in our case. It could definitely be turbulent. It will definitely be turbulent. It's a fan. They're always turbulent to some extent or another. They do a very good job of mixing up the flow. And again, the model, we probably don't want K epsilon because we might get flow separation, and we want to have an idea of when that occurs a little bit more precisely. So we'll select K omega. And I think that really is probably everything we need.
Do we care about gravity or no?
Which way would gravity be going?
Well, in theory, down all over the place.
Which way is the fan mounted?
Well, I mean, down right there. Yeah. Fair enough.
You could bolt a fan any which way you want, right? And theoretically, gravity only matters when you're not forcing the flow. If something's forcing the flow, gravity, or you're not adding tremendous amounts of heat, gravity's effects are typically very weak. So we probably don't need it for this case. Almost certainly. And again, I have to like shrink this window to find the close button. Now, let me see here. We need to basically tell it that it's rotating. Like, well, actually, hold on. Let's go back a second. Let's look at our regions. We have an inlet and we have an outlet, right? Let's set them accordingly. We have our inlet. We're actually going to make this a stagnation inlet. This inlet is not what moves the flow. We expect flow to be coming in through here, but the fan's rotation is what drives the flow, not the inlet. And I want to prove this point by doing this right now. So the inlet is just a stagnation inlet. The outlet is just going to be a pressure outlet, and everything else is a wall. It's a solid surface, flow cannot move through it. Let me save. So theoretically, if we just tell it to run, it should run, but let me pull up a pressure scene, or let me pull up a vector scene really fast. Let me move this over a little bit so you can maybe see a little bit better. I realize it's hard to see up there, I apologize, but this is the room they gave us. Where's my vector scene? Glyph, line arrow, convolution. Well, it's definitely running. Oh, there is no velocity. There's literally nothing forcing anything. Let's just make sure this is working properly. Just for grins, we have our inlet. Let me turn up the pressure to like, I don't know, 50 pascals or something. And let's tell this to run again. Hey, we've got flow moving. So it clearly wasn't that I broke something and we just weren't looking at anything that mattered, right? Although, as a matter of fact, it just aired out and broke. But that's an entirely different thing because I gave it unrealistic conditions. It's just that there's no flow moving. There's absolutely nothing forcing the flow to do anything right now. Which is perfect. That's, if you just put a fan on the table, no air is going to move through it, right? That makes sense. It's not rotating. We need to tell it to rotate. This is kind of the last part, honestly. We did everything else set up with a mind towards letting part of this rotate. That is the entire point of having this center region, is so we can tell this center region that you are rotating. We need to go back down to tools. There is a folder in here called reference frames. Within that, there is a lab reference frame, but we can also create a new rotating reference frame. This is a way of modeling rotating machinery called moving reference frame. MRF is how I've heard it abbreviated. And it's literally creating a reference frame that is rotating with respect to another one. So we can say that this reference frame is rotating about our fan axis. We can select the coordinate system it's rotating in, which is not laboratory because that's not centered on the fan. It's our fan axis coordinate system. And it's rotating in about what axis, about what origin. Theoretically, we could have just given it a new origin. We didn't need to create a new coordinate system, but creating new coordinate systems helps keep you sane, so I do recommend doing it. And we get to tell it how fast it's rotating. This is where you got to be really careful to make sure it takes your units properly, because if you tell it 500 RPM, that's very different than 500 radians per second. It's almost an order of magnitude difference. So let's give it 500 RPM and see what it says. It definitely did say 500 RPM. You can't read it, but it says 500 RPM, not radians per second, so that's good. And this is a reference frame. And let me rename it. Rename I'm just going to call it the fan reference frame. I swear this should be the last thing, is we just need to tell the rotor that it has a new reference frame. Its reference frame has changed. Where is that? So I believe this is under physics conditions. Physics values. Yes. So for our rotor region, air rotor, we have physics values. Under physics values, there's an axis. Don't worry about that. But importantly, there was a motion specification, which is by default stationary in the lab reference frame, which is fine because most things are stationary in the lab reference frame. This one, where is... I named them so similarly I almost couldn't tell the difference. There are two of them. There is a fan reference frame and a lab reference frame. We're going to tell it that it is stationary in the fan reference frame all of a sudden. There are almost certainly several different ways of telling it this. This is the way I know, so this is the way I'm teaching you. But theoretically, now this thing should know that it's rotating at 500 RPM. And oh, hey, look at that. If we tell the simulation to run, it's figuring out that, yeah, flow is coming in and flow is being shoved out through the outlet here. And it looks kind of weird, honestly, because it's figuring out how these reference frames are interacting. But literally all we've done to force any of this flow is just tell it that that inner region is rotating. And it's doing that, everything else based on that. Now, is this a particularly good fan? I don't know. I did my best to emulate one that I saw online, but I have no idea how fast that thing rotates. So 500 RPM is probably a bad number, honestly.
Are you on velocity or on pressure?
This is velocity.
Okay, because I'm getting like a lot more built up around the top and not so much around the bottom, interestingly enough. Like here's where I'm at.
Are you looking at pressure?
Oh, also velocity.
No idea. It's figuring out. What iteration are you on?
For 500.
Yeah, this is only on like iteration 150. Okay. So give it time. I think yours is just running faster because this laptop is not very fast. But it is figuring out what's going on slowly. Again, the only thing that it knows is that the air is coming in at 0 pascals if it's stationary. It's actually not, so it's coming in at a slightly lower pressure probably. And then it's getting driven by these fan blades and then spat out that outlet. Again, just to prove a point here, if I stop this, just save it really quickly before I forget, and clear this, and go back down here and set our reference frame to 0 and tell it to run again, it does nothing. Literally all of that is just telling it that it's rotating at some speed. All of it. Again, this is a semi-random blower type fan, so no promises on exactly what performance we can expect out of it. But it is absolutely able to predict some amount of performance based on the geometry that we have. That is a way to do a rotating lab reference frame in, about 2 hours, a little bit less. Again, admittedly, I didn't expect anyone to necessarily follow along the full process. Good job on keeping up, by the way. I was not expecting that to work at all. But this is, according to this, still recording. And it can hear me, so that's good. I might be quiet, but it can hear me. So, are there any questions that anyone would like to ask about probably conceptually what the process looks like rather than where any particular button is? But, yeah.
conceptually about the report, when is it due?
That is a good question. On one hand, this is complicated to set up. On the other hand, well, you've seen it doesn't take very long to run
Yes.
compared to some of the others. Yeah.
On the third hand, 295 students have our update on the 30th, like our next chapter update. So if that would be taken into consideration, that would be really fine as well.
So noted. That is a fair consideration since this is a graduate course. Oh, wait, I never actually changed its value. Well, this is still iterating, so let me give it 1500 RPM and see what happens. One thing to note is you might need to ramp up the RPM. If you give it like, I don't know, 5,000 RPM, it could theoretically work. But if you just give it 5,000 RPM, it might break. So you might need to give it like 500, 1,000, 1,500, 2,500. Let it run, a couple hundred iterations in between each step change. If you get really creative, you could write a field function that ramps it dynamically based on iteration. So it'll just do a ramp of fan speed based on iteration. So it like starts at 0 and it ramps up and then it stops increasing at iteration 500 or something. But I digress. It'll be doing, I'll say this, certainly after the 30th, by a few days at the least. I will post an assignment on Canvas and I will take that into consideration. That said, exactly what the scope is. It is this fan. And I did also literally walk through it. But we will look at different speeds. You will look at multiple speeds, actually. So for these purposes, more or less what we're going to be doing is varying the fan speed, for one. And also varying potentially the amount of back pressure that could be experienced. Because let's take a fan, for example. Again, if you try and move air through a filter, it's going to move a lot less air than if you just put it on the table and let it move air, right? So the filter is a case with higher resistance, and they just put it on the table and let it run as an example of a unrestricted or free flow fan performance. So principally, it will be this fan, but we'll look at, again, a couple of different speeds, which are TBD. I will post that when I post the full assignment, as well as potentially a couple of different back pressure values. Basically, it could present some amount of resistance to the flow. And I need to figure out what the best way to do that is. But I will tell you what the best way to do that is in that assignment when I post that. Incidentally, it does seem to rather be starting to match generally the profile that you saw once it actually gets up there. Of course, I also am running at 1,500 RPM now, so, yeah, pretty much.
I mean, that makes sense, though, in theory, that you would have.
But in any case, so again, multiple fan speeds. And keep in mind, you might need to tweak the mesh for different fan speeds. There's no promises that any one mesh is going to be fine down at 500 RPM and also be fine up at 5,000. It might need to be tweaked. It's a function on what does your flow rate look like, really. So, but different RPMs and different potential flow resistances, which will be posted with the Canvas assignment. And it'll be due in a couple weeks, again, taking the 30th into account for those of you that care about doing Halloween things, and also for those of you who have 295 stuff to write. Yeah, been there, done that. I'm conceptually aware. That said, are there any other questions on presumably the conceptual process, but I can do my best to answer questions about some details as well? Not yet? The concept makes sense to people? Yep. Again, to highlight the really big differences is that, or the biggest I would say, is it has to be set up, your regions have to be set up in such a way that you have a specific region that is allowed to rotate. If you do not have a specific region that is allowed to rotate and it is separate from the others, this is not going to work. So we made a completely separate region for that. And then more or less we set it up like we normally would. We had an inlet with some conditions, an outlet with some conditions, and we told it that that rotating region is rotating by specifying a different reference frame. Like I said, it is a moving reference frame simulation. It's not physically moving the blades at all, but it's acting like they're moving based on reference frame math. I refer you back to dynamics for all that good stuff. But as applied to fluid mechanics. So, again, if people, well, are there any other questions on any of this at the moment? If you would like to attempt to work through part of it right now, feel free. It is about 10 minutes past 5 o'clock, so you've been listening to me chatter on for 2 hours at this point. That must be trying to put many of you to sleep. If you would like to try and work through it for the next 20 or so minutes, maybe closer to 30 minutes, free game until the end of the class. If you have questions, I'll be here. But if not, then that is the end of class for today. And again, I will post the full assignment, but it will be using this geometry. So, in theory, you're off to a really good start.
Oh, thank you.
And in theory, anyone who's here should have a really solid start on it. Well, I mean, have a really solid idea of the concept at least. But one thing that might need to happen is there might need to be an extension on that.
Oh, on that.
Yeah.
Would that be super hard to alter from that?
It would. You would add a separate region. It would be downstream. Yes, potentially, but that's if you can get the fan working. That part is really easy.
Okay, cool. Thank you.
You as well. What's up? Right, yes. Let me go ahead and do that now. So more or less what I'm going, I presume since you tried to submit it, you're ready to try submitting something? Is that correct? Okay, so what I will do is I will change that up through midnight tonight. So just whatever you got, submit it by then. I'm a little bit. What was the due date on this? Wait a second. It said you couldn't submit?
Yeah. No, not this one, the first one.
Oh, the first one.
It was actually closed 2 days post the due date.
Okay, well, same principle. And fundamentally, well, 3 days, but yeah. So again, I will make this, screw it. I'll make it due tomorrow. Submit it.
I have it ready. I could just.
Well, it doesn't matter. It's tomorrow just for the sake of margin. Submit that and then send me another Canvas message when you've got that submitted.
Oh, thank you very much.
Yep. What's up?
I had a question about the comments for the assignment.
Assignment 1, I assume, yeah?
Yeah.
Yeah.
One of the comments was that my figures were messed up. Like you said all the figures were before like anything else. I checked my PDF and my doc file and I couldn't get that to show up on my end.
Let me take a look.
Because that did show up for me once, but I deleted them.
So, sorry, what's your name?
Jason Segara.
Well, let's just take a look really fast.
Yeah, because I had that issue before, but I thought I fixed it and I couldn't get it to show up again on my end.
Okay, well, this is what it looks like for me.
Oh.
You see what I mean? So let me go ahead and try and download the PDF and see if that fixes it. Oh, that's interesting. So yeah, the Word document messes it up, but this one doesn't. Okay, that's fair. Well, that addresses one of the points at least, sort of. Um, um,
The other one was just I need to address the Reynolds number and somewhere in the.
well, yeah, I don't recall you having particularly mentioned. Also, just as a note, this is well, up here, this is a pretty serious discontinuity in prism layer agreement. It agrees much better down here, but I don't expect you to fix it necessarily. Don't worry about rerunning the simulations or anything, just as a point of, if you get a scenario like this, you probably want to have a slightly thinner prism layer. So it might have slightly a worse agreement back here, but then it would agree better up there. So I would just make that prism layer a little bit thinner.
Got it, because that's the focus mainly. So
because you get really large gradients right up here. You do still get gradients back here, but less severe.
Okay.
So if you have a choice of getting the prism layer to agree, the boundary layer prism layer to agree really well, get it to agree, if you can only get it to fit in one spot, or get it to fit really well in one spot, get it to fit where you have the highest gradients, which we expect near the leading node of an airfoil.
Okay.
I guess the other point was, what Reynolds number was this at?
I thought I ran it. I think you said the maximum was.
I gave you a Mach number max and a Reynolds number min. What Reynolds number did you actually run it at? Because I believe you had a line in here was along the lines of it was run at more than 500,000 or whatever. Maybe it wasn't here. I forget where it was exactly.
I know the Mach number I set to the max of what you defined, and my Reynolds number was. I thought it was slightly above the minimum, but.
Did you crank down the density?
I don't think I did.
Because at sea level, I'd expect 0.3 Mach to be way the hell above 500,000. I'm just the thing that threw me is that this is really not particularly characteristic of this airfoil. Like, it drops fairly rapidly, but not that rapidly. Like, you went from, in a matter of 2 degrees, right?
Yeah.
You went from 1.4 down to 0.4. You lost a full integer coefficient of lift, which would be the equivalent of this thing. Like, if this were at like 14 degrees, it would go from there down to like there.
Yeah.
Like, that's even steeper than this slope here. So that's why I'm curious, because you only selected a couple of the Reynolds numbers graphs off of airfoils, which is fine, but the behavior of the stall doesn't even match. And also, it's very different from what other people got.
Okay.
Most people up at the similar angles of attack, if they experienced a stall, it was a very gradual stall. It wasn't all at once. And this almost ultimately traces back to
The mesh.
Reynolds, or to the prism layer specifically.
Okay.
Now, admittedly, a large, and you've also got really weird, sharp discontinuities. Also, pitching moment about what? Was this the leading edge? Was this trailing edge? Was this quarter chord?
I think it's quarter chord.
Doesn't look like quarter chord because it's positive.
Oh.
I expect a negative pitching moment about the quarter chord. Oh, I know what it was. I think I might know what it is. You probably specified the z-axis, right?
Yes.
Was it positive or negative?
I think it was. It was negative.
Okay, well, if it's negative, then I'm confused. If it was positive, then that makes sense.
I don't remember.
Well, see, the issue is the way airfoils have their coordinate system at moments defined is that if we're looking at the quarter chord, well, technically your coordinate system is anchored up here, right?
Yeah.
But if you look at your quarter chord moment, so 1/4 of the way, you look at moment here, you're looking at about the z-axis.
Yeah.
Well, what is a positive moment? Right, you think that. Nose down would be positive.
Yeah.
Airfoils use a different nomenclature. that is a positive moment for
Yeah.
anything concerning airfoils. Nose up is a positive pitching moment, nose down is negative.
Yeah.
So I suspect that might just be flipped in your case. And this can happen if you just tell it to give you the moment about the z-axis.
That's probably what I did.
If you ask for it about the negative z-axis, it'll sign flip that automatically.
Okay.
But a lot of the reason for the one was the fact that the stall behavior is weird, but that's not enough bias. It was mostly that I just thought you completely disregarded where the hell the graph should be, because it displayed that really weirdly.
Yeah.
So for the sake of argument, like, honestly, it's acting a little bit weird from simulation perspective, but it was mostly I'm zoomed in. That's what's going on. It was mostly saying fix the formatting, but the formatting is borked, not because of anything you did, just because of the way the preview worked.
Oh, that's weird.
Yeah, because again, if I look at the PDF, it's fine. So if anything, this makes me just want to specify only submit PDFs for the future. But yeah, no, honestly, I think that is fine. I'll bump that up just right now because
Okay, cool. Thank you.
it was primarily the thing that will irk me substantially is that if people completely ignore the format instructions, which it looked like you did, but that was just the document messing up. So you didn't actually mess it up. So don't worry about it. Again, the behavior aerodynamically is a little bit weird. So I would be mindful of that for any future forays into CFD, is that that's a pretty serious difference in stall behavior.
Okay.
But you don't need to revise or resubmit or anything like that.
Okay. All right. Cool.
Just be mindful that it was doing weird things aerodynamically. Don't look at that and say, this is perfect. I need to do nothing else for any different airfoil simulation ever. It's good, but it's definitely got some weirdness going on.
Okay. And then I had a question about the second one. For my heatsink, the spacing between the fins, it has 1 millimeter. So it was heating up like really like a lot, and it wasn't.
How
really
thick were the fins?
5 millimeters.
Oh, okay, so you had a gap thickness that was substantially smaller than the order of magnitude for your fin thickness.
Yeah, so I was getting really.
That will result in weird behavior from a conceptual standpoint. Like, it's going to get hot because it's going to be hard for flow to move through that gap, which is going to make it hot, but doesn't fundamentally make it invalid necessarily.
It just took a lot longer.
You're going to need more iterations and a finer mesh. Correct, yes. So was that necessary? No. Is it still perfectly acceptable? Yes.
Okay.
To answer your question, I clearly haven't gotten them graded yet.
No, yeah, I was wondering because the sphere and the pins I was getting convergence really quickly, but my heatsink, it was taking like.
Yeah, so how close together were your cylinders for your pin fins? My guess is your gap was about 5 to 10 times bigger.
Yes, it was like around 5 millimeters, 6 millimeters. Yeah.
Whereas your gap between plates. So it's a two-pronged thing. The first part of this entire thing is that you had a lot more cells because you needed to get cells into a small gap.
Yeah.
Which is only natural. If you have a really small gap, you need 3 cells in a gap. That means each cell needs to be so big. That just makes your cell size really small, which gives you lots of them. That's fine. So it takes longer to do an iteration because you have lots of cells.
Yeah.
The other side is because you have lots of cells, there's lots of interactions between those cells because there's lots of cells. So it takes you more iterations to converge.
Yeah.
Because if you have, where did I put that whiteboard marker? There. I'm not going to worry about it too much. If you think of having a whole bunch of cells in a row, well, if this cell changes, in order to change this one, it has to change that cell, that cell, that cell. It has to change them all in a train.
Yeah.
If you only have 2 cells and this one changes immediately. So that means basically you need more iterations to get the same change, and each iteration takes longer because you have more cells. So it gets into a feedback loop. So
Okay.
that is expected
Okay.
based on what you've described of your scenario. Stop it.